Hello, I'm Emma Ortega and I'm going to work on a problem consisting of subspaces in R3. Before we start, we should recall the definition of a subspace. If S is a non-empty subset of a vector space V and S satisfies the following closure conditions of scalar multiplication and addition, then S is a subspace of V. The problem I'm going to work on states, determine whether the following sets form a subspace of R3. So we have four different sets. Let's start with part B. Later you'll see why. We have the set of vectors x1, x2, x3 transpose such that x1 equals x2 equals x3. And let's call this set B. First, we should check if the set is empty. If you remember from the definition, we have a non-empty subset and the two conditions. So we basically have three conditions to check. To check if a set is empty or not, we have to check if it includes the zero vector, satisfying the conditions we were given. The conditions are that x1 equals x2 equals x3. So for the zero vector, we have that 0 equals 0 equals 0, which is true. It satisfies the condition, therefore the set is not empty. So now we go to the next condition, the closure condition of scalar multiplication. And we write that x, b, and b, where x equals x1, 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 and alpha is natural. So then we do scalar multiplication and we get alpha x1, and alpha x1. We can see that x1 equals x2 equals x3, so the vector is in B, therefore it is closed under scalar multiplication. Now we go to the second closure condition, which is addition. So we write that x and y, b and b, where x equals x1, 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 and y equals y1, y1, y1. We check their addition and we get x1 plus y1, x1 plus y1, x1 plus y1. We can see that x1 equals x2 equals x3, so the vector is in B, therefore it is closed under addition. Since all three conditions were satisfied, we have that B is a subspace in R3. Now let's go back to our first part A. We were given a set of vectors x1, x2, x3 transpose such that x1 plus x2 equals 1. And let's call this set A. Now first again we check if our set is empty with the zero vector. We are given the condition that x1 plus x2 equals 1, but if we check the condition with the zero vector, we have that 0 plus 0 does not equal 1. Therefore, the set is empty. Since the first condition doesn't satisfy, we can already stop here and say that A is not a subspace in R3. Let's go to our third part C. We have the set of vectors x1, x2, x3 transpose such that x3 equals x1 plus x2. We can call this set C. Now again, we first check if our set is empty with our zero vector. The conditions are that x3 equals x1 plus x2. So for the zero vector, we have that 0 equals 0 plus 0. It satisfies the condition, therefore the set is not empty. Now we go to our closure condition, the scalar multiplication. So we write, let x, b, and c, where x equals x1, x2, and x1 plus x2, and alpha is natural. So we do scalar multiplication and we have that alpha x1, we get alpha x1, alpha x2, alpha x1 plus alpha x2. We can see that x3 equals x1 plus x2 because alpha x1 plus alpha x2 equals alpha x1 plus alpha x2. So we get that that vector is in C, therefore it is closed under scalar multiplication. Now we're left to check our second closure condition, the addition. And we write let x and y be in C, where x equals x1, x2, and x1 plus x2, and y equals y1, y2, y1 plus y2. If we do their addition, we get x1 plus y1, x1 plus y1, and x1 plus y1 plus x1 plus y1. We can see that x3 equals x1 plus x2 because they do equal to each other. So we have that vector is in C, therefore it is closed under addition. Since all three conditions were satisfied, we have that C is a subspace in R3. Now let's do the last one, part B. we were given the set of vectors x1, x2, x3 transpose such that x3 equals x1 or x3 equals x2, and let's call this vector b. Since that's OR, it means that at least one of them has to be satisfied, either x3 equals x1 or x3 equals x2. And so again, we start with checking if our set is empty with our zero vector. Conditions are that x3 equals x1 or x3 equals x2. So for the zero vector, we have that 0 equals 0 and 0 equals 0, which is true. So it satisfies the conditions, therefore the set is not empty. Now we check our closure condition of scalar multiplication. We write that x, b, and d, where x equals x3, x2, x3, and alpha isn't natural, is natural. I wrote x equals x3, x2, x3 because I followed the first condition that was given, which is x3 equals x1. We could have used the x3 equals x2, but it doesn't matter. You can choose either or. So we check the scalar multiplication and we get alpha x3, alpha x2, alpha x3. We can see that x1 equals x3, so it is in B, therefore it is closed under scalar multiplication. And now we're left to check our second condition, the addition. And so we write let x and y be in Z, where x equals x3, x2, x3, and y equals y1, y3, y3. I wrote them this way because we were given two conditions that either x3 equals x1 and x2 equals x3. So both of those vectors are in B. So now we check if their addition satisfies. So we get x plus y equals x3 plus y1, x3 plus y3, and x3 plus y3. We were given the x3 and x1. x3 equals x1 or x3 equals x2. So it has to satisfy at least one of the conditions. So we get that x3 plus y3 does not equal x3 plus y1, nor x3 plus y3 does not equal x2 plus y3. Therefore, the closure for addition does not satisfy. Since one condition did not satisfy, D is not a subspace in R3. I hope this helps you. Thank you.